Now let's look at the Norton Thevenin equivalent circuits. And here the setup is I have two sub-circuits, kind of conceptual representation of the actual applications. And if I have sub-circuit 1 connected with sub-circuit 2 at this interface of the pair of nodes A and B. Okay. And in the actual applications, you may have a very complicated system. Let's see the power grid, right? And you have something plugged into the wall, the outlet there, and you're trying to model what is behind that wall there. That's a huge power grid, right? In many cases, we can simplify that by replacing that complicated. It's hardly known, right? But we can measure sometimes. And by replacing that with a very simple circuit, what we call the Thevenin equivalent circuit, which is the voltage source. And by the way, I'm using the capital one to the bold fonts in some of the figures to use interchangeably as the phasor notation with the vector overhead. Okay. And the Thevenin equivalent circuit is voltage source in series with impedance. Right? The Thevenin impedance, we use subscript T to indicate the Thevenin equivalent impedance. And the prerequisite that you can do this is this subcircuit if the subcircuit number 1 is linear. As long as linear, you can do this, which is intuitive, very understandable, right? Because if a nonlinear circuit, and if the Thevenin definitely becomes linear, how you can just magically turn a nonlinear circuit into a linear circuit if it was originally not linear. Okay, so this transformation or equivalence does not depend on whether subcircuit 2 is linear or not, right? Even if you have nonlinear circuit, you can still do the Thevenin equivalent for the subcircuit 1 as long as subcircuit 1 is linear. Okay, so that's for the Thevenin. And for Thevenin equivalent circuit, let's see if we have this Thevenin equivalent circuit inside, what would be the voltage and current at the interface? Let's see, this is voltage, this is current. And in this case, we can write the equation of, so let's see, the voltage across this impedance is going to be I times Z sub T1, right? So this is the this I, and the way I label that voltage following the passive sign convention. Therefore, I have that. And now I can use the KVL. The KVL says the V, which is, let's choose this direction. So in that case, this V here is voltage drop from positive to negative, right? So from positive to negative, I have voltage drop. That should be equal to the sum of voltage rises. And this one here, from plus to minus, from minus to plus, that's voltage rise. So that will be V sub T1. And another one here, from plus to minus, that's a voltage drop. We need a voltage rise, so we need to put a negative sign on that. So then minus I times Z sub T1. So this is the sort of a terminal voltage current characteristic for the Thevenin equivalent circuit, right? And we can do for the not alternatively, we could do for use the Norton equivalent circuit. Norton equivalent circuit is if you have a current in parallel with an impedance, and in this case, the same condition is if the subcircuit number 1 is linear, then we can replace that by this Norton equivalent circuit, which is inside this dotted box here. And we have V and I. In this case, for the Norton equivalent circuit, we have, in this case, the voltage V is going to be equal to voltage here, right? And this voltage here would be equal to this current. And this current is based on the KCL. So this leaving current is going to be equal to inner currents, the sum of inner currents, right? So let's call this I. and this I sub x, this I here would be equal I and I sub n1 minus I. So in this case, for this one here, the V is going to be equal to the current that I sub n1 minus I times Z sub n1. If I multiply this out, what I get? I get I sub n1 times Z sub n1 minus I times Z sub n1. So for these two equivalents, for this two circuit to be equivalent, what condition we need to have is that this term should be equal to this term, and the coefficient in front of I should be the same, right? So for this, these are two equivalent circuits. Equivalent circuit, two circuits are equivalent means they have the same VI characteristics, right? So therefore, we need to have Z sub T1 is equal to Z sub N1. This is the coefficients in front of I's in these two equations, and also the other term is V sub T1 should be equal I sub N1 times Z sub N1. Actually, if you're familiar with the source transformation, this is exactly kind of the source transformation, right? But in any case, so these are two conditions you should have, and also in this case, Z sub O, you can see Z sub N1 is equal to V over Z sub N1 is equal and then equal V Z sub T1 is also, so we can write these two equations in one, and that should be equal V sub T1 over I sub N1. And this is the foundation of how we can find this equivalent the parameters for the Thevenin and Norton equivalent circuits. Let's look at the first one here. Is the way we find the Thevenin voltage is by using the open circuit voltage. So this VOC we call the open circuit voltage. And this is another thing really confuses students. Open circuit voltage. What I mean open circuit voltage is I literally take this sub-circuit number 2 off the picture, okay, completely remove it. And once I remove it, and here nothing is connected to these parallel nodes, therefore the current here is 0 amps. Therefore, if it is 0 amps, that means VOC, if you look at the equivalent circuit, if it has 0 amps, I equal to 0, that means the open circuit VOC would be equal VT, right? So therefore, the VOC, the open circuit voltage VOC, is going to be equal to V sub T1. Okay, that's how we find the Thevenin voltage. And another way, the way we find the Norton, the current is we do the short circuit. So we do the short circuit current, and look at this short circuit current means after I remove the sub-circuit 2, now I draw a short circuit line between these. I use a kind of short circuit wire to connect the node A and node B. So in this case, if you look at the Norton equivalent circuit here, and if I short these parallel nodes, what would happen? The voltage across the Z sub N would be 0. Therefore, the current across that would be 0, and therefore the current I would be equal that current I. So in that case, the short circuit current would be flowing between the A and B. That would be equal to the current I sub N. So in this case, that's how we find the Norton equivalent current. I sub N called I sub n1. Okay, so once you find these, right, and you the z sub t1 and equals z sub n1, that equal the VOC over RSC, or the VT1 over I sub n1 we said. Right, so that's how we find these parameters for the Thevenin and Norton equivalent circuits. Basically, you need to find the open circuit voltage and short circuit current. This is the most general method that means applicable to any circuit linear. And there's another shortcut to find these impedances is if there's no dependent sources inside the subcircuit 1. And then when we find this impedances by looking back. Looking back means we turn off, so let's see the subcircuit, and we turn off the sources off. The sources off, we turn and we look back. We look back to find the impedance. So this is going to be Z sub T1 and Z sub N1 the same. And we just find the equivalent impedance. Right? Basically, series parallel connection of impedances. Right? That's only correct if there is no dependent source. Dependent source means voltage control the current source, voltage control voltage source, current control current source, and a current voltage control current source. So those 4 different types. If there is those kind of source, and you may get the correct answer, you may not. So it's not always correct. Okay, I will stop this clip and start another one to take a look at an example. Okay.